Can we start our session?
Okay, sir.
Okay. Now, in first two units, okay, in first unit we were talking about the power electronic devices. Okay, in second unit we're talking about the converters, DC AC to DC converters. Okay, so basically it's a rectifier. So we have been doing so many things that how do you convert from one form to another form. So initially in first one or two classes, I have already told you that there are converters, okay, which converters are mainly to convert from one form to another form. Sometimes we require a DC, sometimes we require AC, so we can convert from one form to another form, okay, using a power electronic devices such as SCR, power BJT, power MOSFET, or GTO, okay, type, tricore. These are some of the things. Now, next unit we are going to talk about chopper. Chopper is nothing but it's a you are converting a fixed DC voltage to a variable DC voltage. In some cases chop the name itself is chopping, means like you are dividing or you're trying to convert from a fixed DC voltage. The input may be this say 220 volt or 24 volt, and your device requires just 12 volt or 5 volt. So you have to convert that from a fixed DC voltage to a variable DC voltage. So these things are required in most of the electronic devices or the power electronic devices. So this means like converting from one form to another form is quite important. Now, if you see, choppers are two types. So before going to this, okay, chopper, I just want to remind you, I know you have done the Laplace transformation. To solve these problems, you have to have a good background of Laplace transformations, especially when you do the analysis part. Till now, I told you in the beginning of the class also that Laplace is quite important application part of the Laplace. Whatever you have done in the mathematics, okay, or even in yeah, it's there in the in mathematics, even in circuit theory, there are certain portions of Laplace transformations are there. So what I'm expecting is that you know the Laplace. So I'm not going back to the Laplace. I'm not going to teach you the Laplace, but you are expected to know the Laplace. So when you do the analysis part, when you go down, while explaining the choppers, okay, you'll come across some of the terms of Laplace. I mean, how do you convert from one form in a Laplace form? So this is it's quite important. So if you are not confident on Laplace, please go through the try to browse in the net, or if you have a textbook, please go through this Laplace transformation so that you don't stop up in the middle. Okay, when I say something, okay, so that from where it came. So that should not happen to you, because these are some of the prerequisite things you should be knowing when you go progress to the higher semester. Maybe this is a prerequisite power electronics is prerequisite for power electronics application. So in power electronics application, you will not be taught all these power electronic devices, stoppers, rectifiers, or inverters. Okay, so this is something like a prerequisite thing. And other thing I just want to, I know some of your friends are not able to join the, please tell them, and yesterday also there were only 22, there should be around 26 to 28 of you should be there. So please ask them to join the online classes. And now let's go back to our unit, that what we are trying to talk on this unit is choppers. These choppers are of two types. One is step down and step up chopper, similar to step down, step up transformer and step down transformers. So there are two types of choppers are there, where step up and step down chopper. And I don't know how can we do the derivation of these two choppers, buck boost, buck converter, boost means the step off, and there is a derivations, and each of these derivations is around 2 to 3 pages. Now what I'm thinking is, if I do it here, I didn't like, what I feel is that most of you are not able to get, even if I do it here by screen mirroring, okay, it's quite difficult for you to, even if I do it here. So what I'm thinking is that I'll, for these derivations, okay, I'll give you I have a copy of this. It must be there even in the textbook, but I have a simplified form of derivations, okay. So I'll just try to upload in the VLE and just go through this. If you have any problem understanding this, Okay, we'll see together. But now, okay, we'll not go directly on the derivation part of buck and boost regulator, but I'm just giving you that there are derivations buck, boost, and buck boost together. There are certain advantages in buck converter, there are certain advantages in boost converter, and if you combine both this together, then there will be formation of buck boost converters. So most of the choppers are using a buck boost. So in step down choppers, output voltage is less than the input voltage. So in step down means buck converter. So output voltage is less than the input voltage. So in step off, it's a boost. The name itself you must be knowing is a boost converter. Okay, step off means that output voltage is more than the input voltage. So these are the broadly classified into two different type of choppers, as a buck converter and a boost converter. And any converters which we are talking about, it will depend on, we'll be using a power electronic devices, and you know the power electronic devices are just a switch. So we are talking about the switch, using a switch. So how long this switch will be in on condition and how long it will be in off conditions, the output voltage will depend on this. So you need to know that which power electronic devices can be used in this type in choppers. So most of the time we'll use SCR in this. So in principle of step down choppers, how do you find out this? How does it work? It basically works on the principle how, at what instant you are triggering this SCR, sequence control rectifier. So when you trigger the gate of the SCR, then what is happening is that if the load is resistive load, and this thyristor is just a switch, it acts as a switch, and when thyristor is on, supply voltage appears across the load. So when it is on, the supply voltage will appear across the load, and when it is off, it does not appear. The thyristor is off, the voltage across the load will be 0. So as simple as this. So you have seen similar type of circuit even in other cases. So this is as simple as this. You have your source is a DC, so you need to have a variable DC output. So this is as simple as this. This SCR act as a chopper, means that at what instant are you triggering this, and when the SCR is conducting, means switch is on, the source voltage will be across the load voltage. So source supply voltage appears across the load voltage. When it is off, the voltage across the load will be 0. Now you must be thinking, how do we get a variable voltage? Step down voltage means like the output is less than the input. Let's say input is 50 volt. The output your requirement is just means 20 volt. Now how do we get this means variable output? So it depends on the on period and off period. So how long are you keeping this SCR on, and how long are you keeping this SCR off? So total, there will be a total time. The whole one cycle, okay, will have total T time. So there will be a certain T on time and T off time, on time and off time. So this is a thing. This is the whole cycle. Total time will be T on plus T off. So this is the output voltage. Okay, total. This is T on time and T off time. So it is in this. Is shown in a square wave. So where T on and T off, this is a total one cycle. So total time will be equals to T equals total T time T will be equals to T on plus T off. So this is the output voltage. Now the current will be in similar way. So current will be V by R. So in case of this is the resistive load. So all these are that BDC is the average value of the output voltage. IDC is the output voltage of load current. T on is the time interval for which SCR conducts. So on time, when SCR is conducting, we call as on time. When time interval when SCR is off, we call as a T off. So total time period will be T on plus T off. And we know that chopper frequency of the chopper switching or chopping frequency is what F is equals to 1 by T. Chopping frequency at what frequency? It means that F is equals to 1 by T. So to find out the output voltage, okay, VDC, this is a source voltage, input voltage. V is equals to input voltage. So VDC will be equals to V T on divided by T on plus T off. So this is known as a duty cycle. T on divided by T on plus T off, total time. So T on divided by total time will be equals to D. So VDC will be V T on by T, which is equals to V dot D. So D is a small letter D is a duty cycle. So T on by T is a duty cycle. So now suppose if you are given a total time and T on time, if you're asked to find out the duty cycle, it's quite simple. So T on will be equals to, means D will be equals to T on divided by T. You must have done, you might have calculated duty cycle in other cases also. So it's similar, just to find out the total time and the on time. So you can find out the duty cycle of that particular circuit. So T on will depend on the whether the STR is on or off. So if it is on, that is to on time, how long the thyristor is on. And the average output current will be VDC by R if it is a purely resistive load. So IDC will be equals to VDC by R. So IDC can be calculated as IDC will be equals to V by R into D. Today it seems the attendance is almost full attendance. 26 of you are attending. It's good that means it's quite important to at least if you just listen a lecture, okay, that it will really help you, and the attendance is compulsory for all of you. So RMS value of the output voltage. We know the average output current, and how do you find out the RMS value? V naught will be root of 1 by T. The integration will be 0 to T on. So integration will be 0 to T on. So V naught square dt. So to find out this, so we know that T on V naught will be equals to V when it is on. When the STR is on, so output voltage V naught will be equals to V. So therefore RMS value output voltage will be, if you write in case of V naught V, then if you integrate this with respect to 0 to T on, then you will get T on divided by T dot V. So output voltage, RMS output voltage will be root D dot V. Please note down this, that RMS output voltage will be V root D dot V, and VDC will be V dot D. So please note down these formulas. VDC equals to V dot D. We'll do some problems related to this. Okay, VDC is equals to V dot D. Duty cycle D is equals to T on divided by T, and IDC is equals to V by R into D, and VRMS voltage equals to root D dot V. Now output power. So output power will be equals to V naught into I naught. So I naught will be equals to V naught by R. Just to rearrange this equation, so output power will be V square by R. So dV square. So we can, even if you know the V and if you know the value of R, if you know the duty cycles, and we can find out the output power. So effective input resistance of the chopper. So what is the input resistance of this chopper? Ri will be equals to V by IDC. So we know that. So IDC, we can, from with the help of IDC, okay, and we can find out what is IDC. IDC is equals to, this is IDC. IDC is equals to V by R into D. Wait with me. It's okay if you have a problem with the battery, okay, there is no electricity, it's okay. So even if there is a problem, okay, we can understand this. So till your battery is drained out, you can just attend. Now if your battery is getting low, so you can go off, it's no problem. So if you replace this IDC V by R into D in this one, V by R into D, then if you simplify this, in place of IDC, if you V by R into D, then if you replace and if you simplify this, you will get R by D. So replace IDC with V by R into D. Then you will get this. You will get this RI will be equals to R by D. So output voltage can be varied by varying the duty cycle. So you know that all this output voltage will depend on the duty cycle. So if your duty cycle, if you change the duty cycle, if you change the T1 time, then your output voltage can be varied. So all these choppers, okay, when you talk about the fixed DC voltage to a variable DC voltage, it will depend on the duty cycle. So if you change the duty cycle, your output will change. So what you have to keep in your mind that your duty cycle will be, it's quite important, it's quite critical in the chopper. So you have to know what is the duty cycle of your chopper. Okay, we'll just do this simple problem. Okay, in a single quadrant chopper, in this quadrant with power from an idle source of terminal voltage is of 230 volt. The load voltage consists of a rectangular pulse of 1 millisecond over the total time of 5 milliseconds. Calculate the average and RMS value of current, a load voltage. Can you please do this and just write your answer in a message? Can you do it quickly? I'll give you 5 minutes. Okay, all of you, I know yesterday itself I told you to be with a pen and a calculator, pen, paper, and a calculator. So can you solve this problem? A single quadrant chopper in a quadrant with a power from an idle source of terminal voltage is of 230 volt. The load voltage consists of rectangular pulse of 1 millisecond over a total time period of 5 millisecond. Total time period is 5 millisecond, and calculate the average and RMS value of the load voltage. To calculate the average and RMS voltage, this is the RMS voltage. RMS voltage is root D into V. Then average output voltage is V dot D. So can you solve this? We know that alpha is equals to T1 divided by T. So which is equals to 1 by 5. So output voltage will be VU will be alpha into VDC. So 1 by 5 into 230. You will get a average load voltage. And RMS voltage will be VDC into root alpha. So root alpha, there is direct application of formula. Okay, I hope this is just an application of formula. Alpha is equal to T1 divided by T, and average value of the load voltage is 46 volt, and the RMS value of the load voltage is 102.85. So just application of formula. If you know the formula, you'll get the answer. So please solve similar type of problems from the textbooks. There are so many problems in the textbooks. So please do it yourself. Now, methods of control. How do you control? The output DC voltage can be varied. Means how do you control the output voltage? Our main focus here is the input is constant and your output should be variable. How do you control this output DC voltage? So there are two different ways. One is pulse width modulation control or constant frequency operations. I'm repeating again, it's a pulse width modulation control or a constant frequency operation. Other one is a variable frequency control. Now, if I elaborate a little bit on pulse width modulation, okay, most of the controlling mechanisms of they use this modulation technique, not AM. amplitude modulation or frequency modulation, but most of the time they use this pulse width of the pulse. You must be knowing that is spike. Okay, the pulse of, so that pulse which can be controlled. The pulse width of the pulse can be controlled. Modulation, I think I have already told you, okay, if you have remembered this, modulation is means the input signal is modulated with the carrier signal. It means that it's mixed with the carrier signal and sent to the other end. Especially this modulation comes in communications, in communication point of view. So modulation is modulating. I think if you have remember, I've given you the example of a horse, your grandfather and yourself. If you want to go from one place to another place, your grandfather requires assistant of, means your grandfather require to go, means that your grandfather may not be able to go to that particular place. So the support is a horse, or let's say a vehicle. So if you want to go to Samjonkar without a vehicle, you cannot go. You cannot walk all the way to Samjonkar. Maybe in olden days, but if just to give you the example, you require a support of a vehicle. So similar way, the input, whatever is the input, to go to that destination, means to reach to that destination, you require a carrier signal. So input signal is modulated with the carrier mixed with the carrier signals and sent to the destination. So where your signals are retrieved back. So retrieve back to the original signal. That same thing is happening with your mobile phone also. You're talking with your friend. Even now, okay, it's happening the same thing. We are using the Zoom. But whatever I speak here, that is converted into digital form or a 0 and 1 form. And that is transmitted. So this is some kind of multi communications, okay, that too many means one more than two people are communicating at the same point of view at the same time and the same period of time. So these signals are converted into digital form, 0 to 1 form, and at the receiving end you're hearing whatever I'm saying, means that it will retrieve back to the original signal. But when it transmits, it is transmitting in the digital form. So your constant frequency is something like this. Your this t is kept constant. The total time period is kept constant, but we are just playing with the t on and t off. So total time period is kept constant. Okay, the frequency is kept constant. Means constant frequency operation means the total time period t is equals to 1 by f. You know this. So it means that f is kept constant. The whole frequency, one frequency, to find out you need to have full pulse width, right? So your total time period will be t. That period t is kept constant, but you are playing with the width of the pulse, means that total t on time and t off time. So you can change this as you require, so that the output voltage will depend on the t on time. So VO output voltage will depend on the width of the pulse. So with t on time can be varied. Other one is the variable frequency control, means that your frequency can be changed, but one of the variables are kept constant. Let's say t on time is kept constant. So if t on time is kept constant and the frequency is varied, then you can change the output voltage. But there are certain disadvantages of using the second one, the variable frequency control. In variable frequency control, what is happening is that when you keep the system on for certain longer durations, then there will be effect, there will be a causes of the harmonics, means that unwanted signal will be generated. Yeah. So that unwanted signal is not required. So your variable frequency control has certain disadvantage. So most of the time they use this pulse width modulation control where the frequencies are kept constant. Pulse width modulation is T on is varied, keeping the chopping frequency F and the chopping period time T is constant. So where the chopping frequency and the time T constant is kept constant. So output voltage will vary depending on the on time. So T on. So how long are you going to keep your switch on, and how long are you going to keep your switch off? So it will depend on these two things. So you have to keep in your mind that pulse width modulations does not have the effect on overall frequency of the systems. It will only have the changes on the period, means like there is some means changes on the T on time and T off time, on time and off time. So it means that there is a changes in the duty cycle. So this is what is happening. Now, if you see here, the total time period, these are the two things, two different type of. Total time period T is remaining constant. Just to give you the comparative study of what is pulse width modulations. Your total time period T is kept constant, but you're changing the on time. Here the on time is less than half of the T, total time period T, and in this case, total time period T on is more than the half of the total time period T. So we are playing with this T on and T off. So it's clearly written in this diagram, in this waveform, that what is a pulse width modulation. We are not changing the frequency, we are just keeping this frequency constant, but we are playing with the duty cycle. Other one is a variable frequency control. In variable frequency control, chopping frequency is varied. It means that time period is varied. This time period is varied. So this time period can be somewhere here, or it can be somewhere here, but the time T on can be kept constant. So to obtain the full output voltage range, frequency has to be varied. So output voltage range, your output is we are talking about the step down, right? The output voltage is buck converters. We are talking about the buck converters. So output voltage can be less than the input voltage. So if we keep the T, one of the component constant, to obtain the full output voltage, frequency has to be varied over the wide range. So frequency has to be varied. So frequency will depend on the total time T. So to obtain the full output voltage range, so this method produces harmonics. So I told you in the beginning that there is certain effect on the output, variable output frequency control. So this method will produce the harmonics in output, and the last T of loads current may become discontinuous. So this method, if you try to keep on constant and even the off for long period of time, then there will be a discontinuation in a system. So comparing with these two types of controlling method of controls, the more advantage is there with the modulation, pulse width modulation technique. So this is what is happening. Your T1 is kept constant in both the waveform, but your total period time T is variable. It means that frequency is changing, variable frequency control. But T1 is, so what will happen to the duty cycle? You must be knowing that duty cycle is equal to T1 divided by total time T. So in this case, T1 is remaining constant, but there is a change in the total duty cycle. It means that there is a change in the duty cycle in this case also. But the problem is that if you keep the T off for longer durations, then there will be a discontinuations in terms of discontinuations in this form. And if you keep the T1 period, there might be some harmonics, generation of the harmonics in the system. So you know that harmonics are the unwanted signal. Now let's go to, now we are going little till now we are just talking the basic of a chopper, how does chopper operates. Now we'll go in detail on a step down chopper with RLE load. All these three loads are, we are not talking about the R load, L load, RL load. Okay, I feel that if you know RLE load, or it means you can understand the other type of load also. So here we have just this is a just simple diagram where we have a chopper, freewheeling diets. You know that what's the function of the freewheeling diet? We have these three different types of load. RLE means RLE load. So we'll say this: when the chopper is on, supply is connected across the load. That we have even seen in previous diagram. So current will flow from the supply to load. Once the switch is on, it will flow from supply to load. Current will flow from supply to load. In this case, this is the current flowing from the supply. This is supply. This is supply is flowing through the load. Now, when the chopper is off, load current continues to flow in the same direction. So even the load current, when chopper is off, it will try to flow in the same direction through the freewheeling diet due to the energy stored in the inductance. So because of the fact that there is energy stored in the inductance, the current will try to flow in the free direction through the freewheeling diet because the energy is stored in the inductors. So load current can be continuous or discontinuous. It will depend on the value of the L. So it can be a continuous load current, can be continuous or it can be discontinuous, and it will depend on the value of L. And the duty cycle D. So you have to be careful that in chopper, duty cycle is one of the most important factors to know the output of the system. So for a continuous current operations, so load current varies between the two maximum. So there are two things. One is continuous current and other one is discontinuous current. In continuous current operations, it will vary from the Imax to Imin. There are two limits. One is maximum current and minimum current. And when the current becomes equals to Imax, the chopper is turned off. So please remember that when the current becomes equals to Imax, maximum current, then chopper will turn off. And once if the current becomes minimum, then the chopper will turn on. So with this waveform, you will understand this. This is the output voltage T on and T off. So current is when from the minimum it goes up to maximum. So when the current reaches maximum, then the chopper is turned off. When this current from minimum to it reaches to maximum, then this chopper is turning off. Now, as soon as it means again what's happening that this current from the maximum, when it goes back to the minimum, when it reaches minimum, then again the chopper is turned on. So this is what it means. From the continuous current operation, the load current varies between the two limits, and when the current becomes equals to Imax, the chopper is turned off. So when it becomes Imax, maximum current, then this chopper is T off. So it will be off. So when it reaches the minimum, then again this chopper is turned on. So this is for the continuous current. So this is for discontinuous current. Current is not continuous. So it reaches to maximum and it is not exactly meeting the at this T off. So this happens when there is a discontinuation in the current. So it is not exactly meeting at T off. When the current is not, there is no, means it starts from here. Even if you see it starts from this 0 point and goes to maximum, then when it reaches to maximum, it will be turned off, but it is not meeting somewhere here. Now, expression for the load current. How do we find out the load current for continuous current operations? So if it's continuous current operation, how do we find out? Now, to know these expressions, first thing you need to know is the Laplace transformation. So if you have a good background of Laplace transformation, you will understand these expressions of a load current. If you do not have this, revise yourself and make yourself key so that it will be helpful for you to understand these things. So this is the conditions when it is load current, source voltage will be across the load, means like when this SR is conducting, this chopper is conducting. So B will be equals to I naught into R K plus L di by dt, right, plus E. So this is how we get the equations. This is simple. Even you have done even in the CTN circuit theory. So if you take the Laplace of this simple equations, V equals to I naught R plus L, to find out the voltage across the load, we can see that V is equals to I naught into R with the resistive load. With the inductive load, L equals to d I naught by dt, change in current with respect to t plus E. Now, if you take the Laplace of this, Laplace transformation of this, you will see V is equals to V by S, then R I naught to S. So you will find out this is the Laplace transformations. At instant t equals to 0, initial current I naught will be equals to I minimum current. So when it is connected, it will be a minimum current on this. So if you take this, okay, initial conditions equals to I naught equals to I mean minimum. If you just replace and if you try to solve, then I naught S will be equals to B minus E. So this is the equation, you get it for this by using the Laplace transformations. So once you have Laplace transformation, then you can take the inverse Laplace transformation of this equation. So inverse Laplace transformation of this equation is this. So please don't ask me how do you get this, because you have already learned how to do the Laplace transformations even in CT and also in mathematics. So please solve this yourself. So Laplace transformation should be clear to you. I told you in the beginning of the class that Laplace transformation is a prerequisite to solve all these things. So this expression is valid for 0 less than t and less than equals to t now, t on. So during the period, chopper is on. So at this period, when it is at this period, the chopper is on. So at the instant the chopper is turned off, then I naught will be I max. With this diagram, when the chopper is turned on, then it will be I min. So when chopper is turned off, so it will reach to the maximum current I max. So this is so at the instant when the chopper is turned off, the load current I naught, that the I naught will be I max. So when the chopper is off, at these conditions, when the chopper is off, when it's equal 0 less than equals to t less than equals to t off, then your source, this V will be equals to 0. So which is equals to R I naught plus L d I naught by dt plus E. So if you solve this taking the Laplace transformation of these equations, then you will get this. So if you redefine the time origin, we have at t equals to 0, the initial condition I naught will be equals to I max. So in previous case, when the chopper is on, I naught is equals to I min, minimum, because at that instant the chopper is on. But when the chopper is off, it means when it reaches to the current reaches to the maximum point, then the chopper will be off when the current reaches to the maximum point. So initial current I naught will be equals to I max. And I naught will be equals to, so if you just solve this and taking the Laplace taking inverse Laplace transformation, you will get I naught t will be I max. So using this is the inverse Laplace transformations. So please, before looking at this, okay, try to solve yourself whether you are able to do the Laplace transformation or inverse Laplace transformation or not. So before looking at this PPT, please solve yourself and see that whether you are able to do the Laplace transformation and inverse Laplace transformation or transformer or not. So expression is valid between 0 less than equals to t and less than equals to t off. So during the period, the chopper is off. So that is the conditions. So at the instant the chopper is turned on, at this period of time, at the end of the off period, the load current is equals to I min. So it means that at the instant when the chopper is on, the load current will be equals to minimum current. So it means that at this instant the load current is equals to I minimum current. It means that at this instant the chopper is turning on. So at instant chopper is off. I think we have already okay. So off. Minimum current and maximum and minimum current. To find out the maximum current, we have seen that I know this equation we have already got it in the previous equations, that when you need to find out the I max, or I mean. So these equations we have taken it from the previous one when the chopper is on and off. So here this is equals to when the chopper is on, right? So minimum current we got it from this I naught equals to B minus E divided by R. So from this inverse taking same equation here. When this is the case, when the current is I minimum, it means that the chopper is in on conditions. So when T is equals to T on, so the duty cycle will be T is equals to dt. So in place of T, you have to replace with dt. So in place of T, I naught T, you have to replace with I max, and in place of T, T is R by L into T. So in place of T, you have to replace with dt. So if you replace this dt here, then your equation will be in this way. So you have to replace this I naught T is equal to I max, and with this RT means in place of T you have to replace with dt. So similar in this one also. So if you replace this, and you will get, so this is the equation you get it. So for equation I naught equals to for I max, similarly T equals to, this is the case when the chopper is off. So you get T equals to T off, and then the T minus T on will be, so in T on, so T off will be total time period. This is total time period minus T on will be equals to T off. So I naught T will be equals to I minimum current. So we'll get T is equals to 1 minus D into T. So in terms of G and T for time period T, so similarly for this we have to replace with 1 minus T. So we are replacing in this two form 1 minus D, and if you try to substitute for I mean, then you will get this, finally you will get this equation. So we have to substitute for I max in these equations, then we get this. So we know that it's a steady state ripple. I max minus I mean is a steady state ripple. And similarly, we get this equation. So same equation what we have got in previous slides. So therefore, the peak to peak ripple current will be I max minus change in the current will be equals to I max minus I mean. It's changing from maximum current to the minimum current. So average output voltage will be VDC will be D dot V, which we got in the previous slide. If you refer to the previous slide, so average output current will be IDC will be equals to I max plus I mean divided by 2. So assuming the load current varies linearly from, so if the load current is varying from minimum to maximum, instantaneous load current is given by, so we can find out the instantaneous load current. I naught will be I mean del with respect to change in the current. So I naught will be I mean plus I max minus I mean into dt into time period, total time period means like into t. So similarly, if we replace this I naught I max minus output voltage in the, to find out the RMS value I naught square. So if you replace with this, then you will get square of means like integration of 0 to dt. Okay, the limit is from 0 to dt. Then if you solve this, you will get this equation, and the RMS value of the output current is this. So even we can find out the RMS chopper current, which is equal to 1 by t 0 to dt I squared t I naught square dt. So you'll get a RMS chopper current also. So chopper current is equal to ICH is equal to root of d I naught RMS current into RMS current, root of d duty cycle into RMS current. So effective input resistance will be R equals to B, Ri is equals to B by Is. Similarly, what we have seen in the previous slides. So Is is the average source current. So Is is equals to D IDC. So Ri will be V by DIC. Okay. So please go through these equations. Okay. I know if you know this, Laplace transformation, it's quite easy. But if you do not have an idea how to do the Laplace transformation, then this question might look quite complicated. But if you know the Laplace transformation, inverse Laplace transformation is quite simple. Just to convert from Laplace to Laplace transformation to again to inverse Laplace transformation. So please go through these equations, okay, and try to redo yourself. So I'll stop here, okay, this class. I'll just take the attendance. Okay. With this, okay, I'll stop here. So can you solve this means these equations and try to do the Laplace transformation and inverse Laplace transformation? So we will meet in next class. I think it's on Tuesday. So then please go through the textbooks and know that okay, all those things, okay, whatever is done, all these examples, okay, how do we do the Laplace transformation, inverse Laplace transformation, what is chopper? It's quite simple. You just have a switch. You just to need to know the on time and off time. With that, you know the conversion, how the fixed DC voltage is converted into a variable DC voltage. Okay,
Okay,
I'll
thank you, sir.
stop here. Take care of yourself. Bye.
Thank you.